Let's think about conservation of angular momentum, where we define angular momentum to be momentum vector cross position vector, where, let's say we have an object of mass m, and it has momentum p, and it's just moving to the right. But we want to evaluate this quantity about some point, which is, say, here. So the r vector is pointing from the location of the particle, which is the origin of the coordinate system in this definition, to that point. And let's say that, so the object just keeps going this way, and maybe there's a distance here, d. So we know that the angular momentum is not changing in time because there are no external forces, and therefore there are no external torques. And so when we look at this, right, we take the derivatives of the individual parts, so it's dp dt cross r plus p cross dr dt, but dr by dt is the velocity, so this vector and this vector are aligned, and there's a cross product, so this must be identically zero, and so this is simply dp by dt cross r, and dp by dt in this case is a constant, so this must be zero, but we can also write this dp by dt as f, using Newton's second law, so that's just f cross r, and the fact that there's no external force means that the torque is zero, so maybe we should write this as, which we define that to be the torque, that must be equal to zero. And so the relationship here is dl by dt equals torque. And we could look at this in terms of a matrix. So the angular momentum is, let's say we choose coordinates. So let's say that x is horizontal, y is vertical, and z is perpendicular to the page. So so we're doing a cross product between momentum and position vector. So I hat, j hat, k hat. The momentum has only a horizontal component. So let's say we give it a speed v naught. So here we have m v naught, 0 and 0. And the position vector, well, we're doing a cross product, but so we have to evaluate this. Maybe we can evaluate it in a simplest situation. So we imagine the particles moving this way. When the object is here, we are at a distance d from that point. And so the vector is that way. So it's easiest to evaluate the angular momentum at that point. And of course, it must be true everywhere. So that's a minus j hat. So it's minus d j hat. And so this is 0, and this is 0. And this gives us minus m v naught d k hat, which we could have gotten from the right-hand rule, applied to, right, p cross r. So p is to the right, and r is, so when the particle's here, it's that way. So it looks like that. So my index finger is pointing to the right, and my middle finger has to point in the r direction. So when we're here, the r direction must be down, and the index finger is pointing this way, the middle finger is pointing down. The thumb, of course, is always into the page here. And so we can see that we always get minus k hat. And it's worth pointing out that when the object is over there, Right, so the object is there. We have an r, that's the r vector, and so there's an r distance that's different from d when the object is here. The distance is d, so this is d, and this is the angle phi in the magnitude of the angular momentum, which is the magnitude of p, magnitude of r, so it's mv naught times the magnitude of this, times, let's call it r, times the sine of the angle between p and r, so it looks like that. And so what we see here is that r sine of phi is in fact d, and that's always true. So as the particle moves away this way and that way, r is increasing, but this quantity is such that r sine phi is always equal to d, as it needs to be.